So, when solving spectroscopy, we ultimately have 4 different types of spectroscopy that we're going to be dealing with. IR spectroscopy, mass spec, carbon NMR, HNMR. I've got them ordered here how I would go through and solve and attempt to complete these assignments. That is entirely up to you how you want to go through and break it down. Okay? So we'll go through each of these kind of individually. So IR, we've now looked at IR a whole bunch of times. You should be able to tell me all in unison at the exact same time what information does IR spectra give you? It gives you information about
Functional groups.
No, I hate that answer. Bonds. It's bonds, not functional groups. Why do I have an issue with calling it functional groups? An individual functional group has multiple types of bonds. Okay? Those multiple bonds have multiple signals. The composition of all of those signals gives you information about the functional group. But the IR only tells you about the bonds. Okay? So when you go through the process in IR spectrum, you should be looking at individual peaks and just playing a matching game with that IR packet that you guys already have. So does it look the same? Okay, that's probably that peak or that type of signal. So when you look at this IR spectrum, what do you see? Okay, not a whole lot of anything except we get a signal here, which happens to be, we've got a carbon to hydrogen bond where that carbon is sp3 hybridized. Okay, if you were in Gould's class, you probably had that whole section crossed out. Okay, so you would then ignore it. Is there anything in there that you should be immediately jumping on trying to solve from? No. Okay, which is one of the reasons why he crossed it out. After you solve the structure, if you want, you can always go back to the IR and try and process that fingerprint region a little bit more carefully, but that's up to you. Okay? So as far as analysis and getting points, this is all we really get out of the IR. Okay? The next thing you could go through and do is look at a mass spec, which you're not going to have to do for at least the group activity. You might have to do for your lab assignment. Okay, you'll probably have to do it in lecture 2. There's 2 primary goals when it comes to mass spec. The first one is to determine the obvious atoms or pieces that can come out of your mass spec. It's where you get bromine, chlorine, iodine, and nitrogen. I'll leave the lecture to explain that. Yeah, you can pick up iodine. The last one would be, your secondary goal would be to get a possible molecular formula. Once you've got the molecular weight, you can roughly approximate what your formula would be running some simple assumptions. One, you probably don't have bromine, chlorine, or iodine, or nitrogen, or maybe you do, depending on the signals that you see. So you can account for those in the molecular weight. The rest of it is going to be made up of carbons and hydrogens. So you can go through and do some simple calculations. For the current problem that we're working with, okay, I'm going to tell you now that your mass spec for this problem is C2H5Br. So that's the molecular formula for this problem. Okay? For your spectroscopy assignment, you'll be told what the formula is. So use that information. Okay? As far as NMR goes, okay, all of these different things get talked about in lecture, but the organization behind it can be a bit confusing. So what I've tried to do is simplify it as best as possible into these 4 primary categories. So when you see any NMR spectrum, the first thing you should be looking for are the number of signals. Okay? And I'm using signals differently than the term peak. We'll talk about that in a little bit too. So we can go through and identify the number of signals. Well, what does that tell us? That tells us the number of unique hydrogens or carbon depending on which spectrum we're looking at. Okay? Unique is really, really important here. It has to be chemically different. Okay? As far as ease of interpretation, all you had to do was count the number of peaks. So that's relatively simple as far as the interpretation goes. Okay? We can then look at chemical shift, which is a slightly larger interpretation, takes a little bit more analysis. It gives you the rough local environment of where your hydrogens or carbons are located. Okay? That information you should be looking up. Okay? I'm pretty sure every lecturer allows or provides a cheat sheet of IR and NMR data. Use that information. Okay? So use your chemical shift much like you would do IR. Does it roughly look like it falls within this range? Yes. That probably means that that atom or hydrogen or carbon is attached to whatever it's referring to. Okay? Because there's a lot of data out there, depending on the chemical shift tables that you look at, students have a tendency to overanalyze it and start putting in all sorts of crazy different structures. Okay? So if you take a look at page 2 of the handout that you should all now have at your desk that summarizes all of those, right in the middle you'll see 2 chemical shift integrations. So flip the sheet over if you guys are trying to find it. That chemical shift range is what I would recommend and what I have memorized. Okay? Because everything else is too variable. All sorts of things can shuffle around. Even those ranges, other weird things can happen within them. Okay? So I memorize those as the bulk ones, and that's as far as I will analyze. Okay? You'll notice there's a giant section that says everything else. So if you get a signal in the 2 to 6 range, what does that mean your hydrogen is attached to? Something else. Okay? And at that point, HNMR, chemical shift information, tells you nothing else. That's it. Okay? The next piece of information, and we're now getting a little bit, or arguably a lot more difficult, is looking at the integration. Okay? The hardest thing about the integration is to realize that it gives you a ratio of hydrogens, not specifically, or the specific number of hydrogens in your sample. Okay? So in most cases, depending on your professors, the ratio is the number of hydrogens, but it's not always true. Okay? So realize that you're getting a ratio, not the exact number. The last one, which is probably the absolute most difficult to analyze, and it usually throws students for a massive loop, okay, is looking at the multiplicity or splitting. This is generating the number of peaks you see for an individual signal. Okay? That information is going to relate or give you some information about the number of different hydrogen neighbors. Okay? Which is kind of difficult to interpret, and we'll look at that as we start to work our way through this. Okay? So let's start with the carbon NMR because it's easier. Okay, so we can start with the number of signals. How many signals do we see here? 2. So as simple as it may be, this is exactly how I would solve it. I would write 2 unique carbons. Okay? Why specify that information? If you leave it blank and a TA has to come through and grade it, regardless of what you draw as a structure, if your carbon NMR is left blank, how much interpretation did you do? 0, which means they give you 0 points for it. So at very least, write down the simple stuff. Get something down there so you're forcing the TA to work. Okay? Next piece of information is moving to the chemical shift. Okay? So when we're looking at carbon NMR, we're looking at the range between 0 and 210 parts per million. So we can drop down the chemical shift line on this. And we can now start to do some more interpretation. How do we figure that information out? What would we do? Pull up the chart. What can you tell me about it? We're looking at alkanes. Okay? So alkanes in conjunction with the now erased 2 unique carbons gives us some information about the structure and now forces the TA to give us some points. Okay? The very last thing that you can pull out of carbon NMR is a very kind of hand-wavy argument, but it works fairly well. So most of the time this comes out. We can look at peak height. Okay? It's a little bit trickier to deal with. Okay? But if we take a look at this, we don't get, so this is the actual spectra for this compound, we don't get 2 perfect lines of equal intensity. Why does the intensity change? We could try and assume that it's the same thing as hydrogen, the number of hydrogen, or the number of carbons, or integration. Carbon NMR removes that information. Okay? It's not easy to get that information when we try and run the spectrum, so we don't have that information. So why do the peak heights change? Okay? It has to do with how easy it is for the spectrum or the instrument to monitor those signals. If a carbon is buried within the structure, it's not easy to detect. And what happens to the number or the intensity of the peak? It decreases. So if you have a shorter peak, in some cases that implies that that carbon atom is connected to more things, or things other than hydrogen. Okay? If you want to use that, you can. It doesn't always work, but it can kind of help you out in rough circumstances. Okay? The last thing you might notice on here is that we've got an extra piece of information noted right in the middle. CDCl3 is a solvent. All NMR spectroscopy, or not all of it, but most of it, deals with adding a secondary solvent. That solvent helps to dissolve and keep your sample in solution and allows the instrument to detect your sample properly. Without that solvent, you get weird spectra. Okay? That solvent could have hydrogens or carbons in it, and because of that, it will also show up in your carbon or hydrogen NMR spectrum. Okay? If you're using CDCl3 or chloroform, deuterated chloroform as a solvent, you see 3 peaks about 77. Okay? And that's what we're showing here. So if you see those 3 peaks at 77, what should you do with that information? You can ignore it. Okay? Most of the spectrum that you'll see both in this class and in your lectures, that solvent peak has been removed from the data. And that's because of where we're obtaining these spectra. Okay? Just be aware that you can see that show up. So now we can move into the more difficult one, looking at HNMR. So, number of signals. What can we write down? We get 2 unique hydrogens. Okay, I know I'm writing sloppy, but it's at least close. Do we have any more information from the number of signals? How many hydrogens are in this compound? Who knows? Okay? The number of signals doesn't tell us that. It just tells us the type of hydrogens. There are 2 types of hydrogens within this structure. Okay? The next thing that we could do is move up in difficulty. We can move to the chemical shift. Okay? The chemical shift for HNMR is looking between 0 and 14. What can we find out now about these 2 positions? So for sure we have a hydrogen bound to something, and over here we have a hydrogen bound to something. What's the something on the right?
Alkane.
Alkane, so we're looking at that atom being a carbon. My personal preference would then to also specify the number of bonds that that atom can hold. How many bonds should carbon have? It should have 4. So I'll show those as hanging bonds. What about the carbon or the structure on the left?
You don't know.
That's in the everything else range. That can be anything. Okay? As far as anything, because it's organic chemistry, we're looking at our halogens, nitrogen or oxygen. Okay? Could it be a halogen?
Theoretically.
You can be a little bit more strict than theoretically. Theoretically not. In fact, not only theoretically, it can't be. Why can it not be a halogen? No. How many bonds can a halogen have? 1. If it's bound to a hydrogen, where's the organic part of our structure? There isn't one. Okay? So it can't possibly be a halogen. So we could eliminate that. At this point, we could continue to move through our HNMR, or we could realize that we have other information. What other information do we have? No, we don't have that information yet. That would be looking at the multiplicity. It's not up there. Nope, also not up there. Nope, well, yeah, we do have that, but we just looked at that. Do you have, say, an IR?
Yes.
Yeah, what does the IR tell you?
It's all alkanes.
It's all alkanes. Do you have an OH?
Oh.
No. So can that atom be an O?
No.
Could it be a nitrogen? Why not? It's not. There's no NH stretch in our IR. How else could we find this? What does our mass spec tell us? C2H5Br. Is there oxygen or nitrogen? No, which means that has to be a carbon. Okay? And I'm not going to draw in the extra bonds because I'm about to delete it all. Now we can take a look at the integration. The integration, a lot of people will relate it to the peak height. That's a very rough approximation. In this case, we can look at peak height because they're perfectly straight lines. Okay? As soon as our peaks split or broaden, we can't look at peak height. We have to look at the area. If we're going to look at the area of a peak, what do we mathematically have to do? Come on, any calculus buffs? It's integrate. We have to integrate the area underneath the curve. Hence, we get integration as the name of this piece of information. So what we can end up doing is comparing those curves to figure out the area underneath them. Okay? In this case, because I drew them as straight lines, we could go through, and because I did it poorly, we can see that there's an approximate joint in each of these. Oh, my pen's failing. Dang it. Okay. What area would you say is under this signal? How many units are there? 2. How many units are in this one? 3. So there's several places we could see this information. We could look at the peak height in this case. Okay. There's something referred to as comparing the curves, which is fairly rare. It's a holdover from old school instruments, and what you would see in your spectrum is something along these lines, usually a flat line corresponding, and then it pops up, and then it flatlines, and then it pops up again. You would compare the area or the height of those two places. Oh, I'm going to have to move to my finger. Dang it. Okay. That's comparing the curves. So if you see those signals, that is ultimately looking at the area. It's a mathematical calculation. Now you can directly compare the height of those two signals. Okay? The other place you can see it is exactly where we've got it written here. A number written underneath each peak. That's also going to represent your integration. The very last place that you can see it, which if you have Dr. Gould, I'm pretty sure this is how he shows it, you'll see 2H and you'll see 3H. What do you think that means? That's our ratio, and it's even better than a ratio in most cases, I think, with him.
Yep. Yeah. With him, it's always exact.
The ratio is exactly the number of hydrogens, okay, in Dr. Gould's class. It doesn't always work out like that. He just happens to be nice. I'm not so nice. Okay? I didn't make the activity, so it's okay. Okay? So, with that information, what does that tell us about our hydrogens? So we said we had a hydrogen bound to a carbon for our leftmost. Our integration says we have to have 2 hydrogens that are exactly the same as this. What's the easiest way to get 2 hydrogens exactly the same? Put them on the same carbon. The other one said 3 hydrogens. What's the easiest way to do that? Again, put them on the same position. Okay? Next piece of information. Looking at the multiplicity. Okay, you'll notice you see the curves showing up on here that I was talking about. Those curves are these things. Okay? And in this case, the information was written next to it, 2 and 3. Multiplicity, it's the number of peaks. The number of peaks are equal to the number of neighboring hydrogens plus 1. Okay? To do that calculation, you have to know what a neighbor is. A neighbor must be less than or equal to 3 bonds away. In most cases, it is exactly 3 bonds away. Okay? In some very rare cases, you can jump to 4 bonds, but that's extremely rare. Okay? And in some cases, you can see it under 3 bonds away. Okay? And that gets pretty tricky. We won't look at those. So if we go back and look at our data again, so let's pick this signal. We said we had a CH2. Okay? How many peaks do we see for this signal? 4 peaks, which means N equals 3. How can I get 3 neighboring hydrogens to the CH2?
If you have a carbon attached.
The simplest way to do it is just attaching it to a methyl. It does not have to be a methyl. Why do we pick the simplest way first? Because it's the simplest. Okay? It is as simple as that. Okay? So in this case, we now have our 3 hydrogen neighbors for that CH2. What about for our other signal? What does that tell us? We still have our CH3, except each of those hydrogens has to be near 2 hydrogens. What's the easiest way to get 2 hydrogen neighbors?
We already have them.
We'll go next to it. So already in the same structure. So let's be careful with that statement. When we're looking at neighbors, if I want to see the neighbors to this hydrogen here, our now circled one, we'll count out the bonds. 1, 2 bonds. Am I at a hydrogen? Yes. Is that a neighbor? Why is it not a neighbor? It is chemically equivalent. Okay? That does not mean it's attached to the same carbon, because that is not always the case. They are chemically equivalent hydrogens, which means we won't count that. So if we count out the next sequence of bonds, we go 1, 2, 3. Am I now at a hydrogen? Yes, that is a neighbor. We can count out again. 1, 2, 3. Am I at a hydrogen? Yes. So within 3 bonds, I now have those 2 neighbors. This is all HNMR tells you. If you're more advanced, you can start to condense the structure, but that gets a little bit tricky to do in some cases. So at this point, I would say hands up, done with HNMR. So what we'll do is now start to compile the data. IR told me CH, SP3s. Mass spec told me C2H5Br. Carbon NMR told me 2 unique carbons, and they're all the alkane class. HNMR told me I had these 2 pieces. Okay, I know a lot of you want to skip, but I don't want you to skip here. According to HNMR, how many carbons do you have?
2.
Count again.
5.
Count again. 4. 1, 2, 3, 4 carbons, according to HNMR. Okay? What does your mass spec tell you? You only have 2 carbons. What does that mean happened in your HNMR? 2 of them were, or you counted your carbons twice. Go ahead and pass it out. Okay? So we need to go back to the pieces that we found from our HNMR and see if there's duplication. Do we have a way that we could condense these 2 pieces together? Yes, which means we can eliminate one of them. How many carbons do I now have according to my HNMR? How many hydrogens? 5. I'm still missing something. So we go back to the mass spec, and the mass spec tells me I have a bromine. How many bonds can bromine have? 1. Bromine's missing a bond. CH2, CH3 is missing a bond. How do I solve? Put them together. Okay? Do not put pieces together until the very end. Okay? Couple things that I want to point out for the group activity before you guys get completely into it. In general, as far as assigning for this assignment, the carbon NMR can be roughly or approximately assigned. Okay? If you want to get really specific with assigning exactly which carbon belongs to which signal, you have to look at resonance arguments to explain that. Okay? So that makes problems number 1 and 2 difficult to assign the carbon NMR for. Okay? Next big issue. If you look at the IR for problem number 1. Okay, well, apparently it's not relevant to you guys, so we can skip on. I'm going to go ahead and draw up the answers to this. If you've got questions, feel free to raise your hand. Raja or I will come by to help you out. And I will solve this one how I would show it. Do you guys have a question?
Do you want to tell us what you were going to tell the rest of the class? I don't know why
Sure.
I woke up this morning.
Look at IR number 1.
So sad.
What do you see?
Push the P, like I don't know why. It's so sore.
So CH237SpectraRecitation hybridized, right?
Yeah.
So let's flip to our NMR. If it was CH237, we would expect a signal between 0 and 2.
Right.
Do you have one? No. So what is your IR telling you?
I don't know.
What happened was that whoever downloaded the spectrum did not look carefully at the background information on where it came from.
Oh.
There was a secondary solvent added.
Oh, okay.
That secondary solvent gives you the CHSP3s. It's not actually in the spectrum.
Just the alcohol.
The alcohol is true, and you should be able to identify another signal that works. And then also,
Can we just draw the line up like that?
that's fine.
Okay.
Yep. And then the last thing that I was going to mention is this one right here. That signal, 3 carbons, 3 peaks
3 peaks for our aromatic.
for your carbon and ammonia.
Oh, no. So I guess. Sorry. I'm not sure what I was thinking about. Oh, yeah.
How are you guys doing over here? Any questions?
I don't think so yet.
Okay, just wandering around.
What's it called? It's an aromatic. Which one? Which one? Nah, I was asking, like, I think that's right. We'll go for everything else. No. I meant, this is a good initial step.
It's like the numbers that you find it tells me we don't know. We have no idea yet.
Do we need it?
No, but it would help us find a structure.
What do you need?
Is that the ratio? We don't know.
You're thinking degrees of unsaturation?
That's what it's called.
It will help, but it's not necessary for this.
Just helps find the structure.
Yeah. If it's something that you've gotten used to doing in your lecture, then you should continue doing that because practice is going to help you for your lecture. But you don't need to do it in this case.
Oxygen doesn't count.
Oxygen doesn't. I think oxygen and halogens don't count. I think. Let's see. No, halogens count as 1 hydrogen.
Okay.
Yeah, but oxygen doesn't count.
Come on.
8 degrees in saturation, so it's probably going to be an aromatic.
Good work. What did your IR tell you?
Why is that unbolded? Like, what is it trying to tell us here? What is
aromatic and then sp3 carbon hydrogens and alcohol.
Does your answer verify that?
Sure, it's only 4 degrees. I got 6.
How do we know Sarah, it's a little how come the doublet triplet is not labeled?
That's again whoever built the assignment. That's their fault for not doing that for you.
Can you fix that mistake?
A little bit. That is going to be a single peak. Those are going to be doublets.
They're both doublets.
They're both doublets. It takes a little bit of practice getting used to reading those, but you can fully expect when you get into lab that you're going to have the same type of thing where those are not clearly mentioned. So try to look for those. So you have to remember the symmetry. So if you grab that sheet for me, flip it over. When you look at your splitting pattern, what the heck happened? Oh, you did that. It's like print it like that. This is the peak shape and number. So if you have 4 peaks, you'd be looking here. Your peak height 1, 2, 2, 1, or is it 3? I can't see. 1, 3, 3, 1. So that means the two peaks on the outside are the same intensity, and the two in the middle have to be 3 times as tall. So if you said you've got side peaks down here, that side peak is really, really short compared to everything else. So that doesn't match the peak shape that that has.
So 1, 2, 1.
So that would be 3 peaks. Do you see 3 peaks?
That's 2. Oh, number of meters.
Yep.
But these
So
aren't really the same
they aren't
magnitude.
the same. You'll always see a shift in the height.
Actually, no.
And this is another tip. If you draw a line connecting those, it's angled that direction. Where's these angled? That direction. They're always angled towards the one that split them.
Okay.
So these two split each other.
Okay.
But yeah, the exact peak height is always questionable. You just kind of have to approximate.
Okay. Thank you.
Yeah, that's nice stuff.
What are we supposed to label on this?
I'll just take the. I'll take the.
All right.
You guys sure you got it all?
Yes.